Hello, everyone. My name is Riley, and I am a graduate student studying agricultural leadership, education, and communications at Texas A&M University. I am currently enrolled in ALEC 640, Methods of Tech Change, and I have been tasked with creating instructional materials surrounding a subject in our class textbook, Diffusion of Innovations by Everett M. Rogers. Since this is an agricultural course, I have chosen to discuss the increasing use of drone technology in the agriculture industry as it relates to Rogers' diffusion of innovations, specifically with the 5 attributes of innovations and rate of adoption that is briefly discussed in Chapter 1 and more heavily in Chapter 6. I hope that you find this subject interesting and that it sheds some light on why technological innovations are or are not adopted by agriculturalists and industry leaders. Here are a few learning objectives that I hope you can achieve from this instructional video. The first one is learners will be able to understand Rogers' attributions of innovations and how they affect the rate of an innovation's adoption. The second one is learners will be able to apply this knowledge by analyzing a current agricultural innovation. And the third and final one is learners will be able to reflect on information by successfully completing a multiple choice and true or false assessment, which will be at the end of this video. Technology and agriculture. In 2015, agricultural researchers argued that it was the start of the 4th agricultural technological revolution. Innovations like sensors, satellites, robots, and other digital technology really began paving the way for precision agriculture, or precision farming. PA is a comprehensive, sustainable innovation systems approach that assists farmers in production management and aims to improve farmer decision-making. This leads us to the challenge of feeding a growing world. In 2014, the United Nations and Food and Agriculture Organization estimated a food production need of 13.5 billion tons per year by the year 2050. And this is almost 60% more than what is produced now. Taking this into consideration, it's pretty apparent why technological innovations are important for agriculture. Technological innovations lead to precision agriculture, which leads to sustainability, which leads to meeting food demands, and much more. So why drones? I don't know about you, but when I think of drones, I think of a children's toy, not an agricultural technology. These drones are often referred to in research and academia as an unmanned aerial vehicle, or UAV. UAVs have been increasingly used in industrial operations and other diversified fields, including agriculture. But the agriculture industry has shown to adopt them at a much slower rate compared to others. According to Murray and other researchers, drones are often used by other industries to do things like supervising construction sites, deliver packages, monitor pollution, provide weather reports, and even assist in first responder activities. Now, as it relates to agriculture, drones can manage water use, pests and diseases in crops. They can monitor livestock herds, survey the range, identify crop damage, evaluate soil condition, spray fertilizers, spot spray pesticides, and so much more, all of which can be done from the comfort of your home office or couch, thanks to UAV technology. On the previous slide, we discussed the need for increased food production, and with that comes an additional challenge of doing so in the most environmentally friendly way possible. Technological innovations, especially UAVs, play a large part in this solution due to their small carbon footprint. Now, while this pretty much explains how drones are impactful to the agriculture industry, I also wanted to show this video where drones are just explained a little bit better by the CEO and co-founder of a company called Helio. His name is Arthur Erickson.
It takes hard work and methodical planning to grow the foods that feed the world. One method used for decades to deliver vital nutrients and pesticides to fields are crop dusting airplanes, but they can be expensive and dangerous. Now, drone technology has opened up a new frontier for crop management. I winged my way south to Houston, Texas to meet aeronautics engineer Arthur Erickson, co-founder of a company called Helio, to learn more about their custom-built crop dusting drones.
So what is the crop spraying drone? Basically, it is a fully autonomous flying machine that automates precision agriculture tasks for farmers and applicators in the agricultural industry.
So what are those tasks?
Pesticide application to protect your crops against bugs or fungi, I should say, fertilizing, even just crop scouting, identifying what issues you have with your crops and how you could help.
You've got to worry about payload. You've got all sorts of tasks that this drone has to do. So where did you start?
We started with the simple engineering questions. What's the cheapest, most effective, and reliable way to get a payload over these crops? So we just kind of built the drones up from there. Part of our development challenge was saying, how do you take this incredibly complicated machine, but make the input controls to it simple enough for someone out in the field to use day in and day out without worry going into the planning process? So Adam, we've got multiple models.
Arthur showed me one of the many drones they build in-house to help farmers achieve healthy crop yields.
This is our AG-122. It's one of our largest models. It's got 8 rotors on it. It can lift close to 300 pounds all up. Right here in the very top here, you've got the brains of the drone. So you can't see them, but in there's a flight controller. So that's where all the artificial intelligence, the machine learning, the intelligent routing, all that is happening right here. Beneath the drone, actually, you've got all the spray system, which is how we deliver the actual chemicals onto the crops.
We loaded up the drone and headed out to a local field to see it in action. Arthur manually controlled the drone at first.
And there I go, taking right off. And here I'm going to toggle the spray. So right now, it is spraying. Again, hard to see, but it is coming out there, and you can see how well it can cover the crops here. That downwash from the propeller is really pushing that mist down.
I was going to say there's a little bit of wind, but I can see the mist going straight down. Now, this you are controlling manually, but one of the great features of this is you can set it on auto and walk away.
Yeah, 99% of the time, this drone's out flying itself.
After a few quick adjustments, the drone was ready to fly autonomously.
Arm and take off.
So you basically just set a predefined area for it to do its thing?
Correct. Give it some boundaries, give it a dosage to target, click takeoff, and it's going to go do its thing.
These are the 5 attributes of innovations as discussed by Rogers in the textbook that you see pictured here. Those 5 are relative advantage, compatibility, complexity, trialability, and observability. All of these will be defined later as we dive deeper into each attribute as they relate to drone adoption. These attributes give us context as to why some innovations are adopted quickly, slowly, or not at all. Closely related to the 5 attributes of innovations previously discussed is rate of adoption, another term coined by Rogers in his diffusion of innovations theory. Rate of adoption is defined by Rogers as the relative speed with which an innovation is adopted by members of a social system. As Rogers explains, the majority of variance in the rate of adoption of innovations comes from the 5 attributes, but other moderators, such as the type of innovation decision, the nature of the communication channel diffusing the innovation, the nature of the social system the innovation is being diffused in, and the extent to which the change agents and opinion leaders promote the innovation also contribute to adoption rates. I included this quote by Heijs van Wolfen simply because I think it speaks a great deal about the way innovation adoption works. It is far from just inventing and disseminating. And as you can see, the quote reads, "You can invent alone, but you can't innovate alone." Now, let's take a deeper dive into each innovation attribute, starting with relative advantage. Relative advantage is defined by Rogers as the degree to which an innovation is perceived as being better than the idea it supersedes. In other terms, what advantages does this innovation have over the one it is intended to replace? In relation to UAVs in agriculture, why are these more ideal than other aerial methods of crop, range, and livestock management, such as helicopters and crop dusting planes? Well, they're more environmentally and economically efficient due to their battery power and cheaper operation costs, as you saw in the video I played previously. They are also smaller in size compared to other aerial vehicles, allowing them to reach, monitor, and service smaller areas. Here's a scenario to give an example. Imagine it's calving season for your cattle herd, and you have cows bedded down in the trees that are due to calve at any time. A small battery-operated drone would allow you to check on those cows in a tight space while remaining quiet and leaving them undisturbed. Also, according to Rogers, relative advantage is one of the most powerful predictors of the rate of adoption. The next attribute is compatibility. Rogers defines this as the degree to which an innovation is perceived as consistent with the existing values, past experiences, and needs of potential adopters. Compared to relative advantage, compatibility is going to be more specific to each individual farmer or rancher considering drone adoption. If farmers or ranchers are already using flying technologies or other above average technical innovations, drones will be more compatible with them compared to someone who still works primarily on horseback. Drones are also going to be more ideal for large-scale farming. So if a farmer or rancher is only operating on a few acres, a drone would not be necessary. In other words, it would not be compatible. Lastly, it may be an important part of one's culture to go outside and put forth their own blood, sweat, and tears whenever possible. And a drone or other technological advancement to replace that could be seen as an insult to that aspect of their culture and their pride. As it relates to rate of adoption, Rogers says that high compatibility translate to a higher rate of adoption, as low compatibility translate to a slower rate of adoption. The third of the 5 attributes we will discuss today is complexity. Rogers defines complexity as the degree to which an innovation is perceived as relatively difficult to understand and use. Rogers states that the complexity of an innovation, as perceived by members of a social system, is negatively related to its rate of adoption. If an innovation is difficult to understand and challenging to use, it simply won't be adopted at a high rate, if at all. The biggest challenge with the complexity of drones is in regard to the average age of a farmer. According to recent United States Department of Agriculture, or USDA data, the average farmer or rancher age is near 60, meaning that the likelihood of them not being comfortable with high-tech devices like drones is very high. This means it would be complex for them to understand and or use. However, since drones are increasingly popular in multiple industries, it has become easier and easier to access training and other usage information for these devices. This would also be a good time for change agents and opinion leaders, which are other terms discussed throughout Rogers' theory, to do their parts in innovation adoption as well. Another complexity issue is the sparse regional restrictions placed on drones. Some regions ban the use of drones because they can interfere with other air traffic controls, which we will mention again here shortly. Trialability is defined by Rogers as the degree to which an innovation may be experimented with on a limited basis. When I think of this attribute, I think of test driving cars or trying on clothes while you shop before you actually buy them. People tend to stray away from any purchase without certainty that they like it or that it works. Because of this, trialability is positively related to the rate of adoption. Similar to complexity, regional restrictions may prevent the trial and experimentation of these UAVs. In the agriculture industry, specifically agricultural extension, field days and conventions are common events where industry leaders and leading companies gather to educate those who are involved on slightly smaller scales. Events like these are good options for potential innovation adopters to experiment with innovations on a limited scale. The final attribute we will analyze in this video is observability. Rogers defines observability as the degree to which the results of an innovation are visible to others. Basically, we want to know if the adopter can see the benefits of the innovation. Observability requires the adoption of the innovation from others in order for results to be visible to potential adopters. Depending on the type of innovation, it can also take years for results to become visible. Rogers discusses the hardware and software of innovations. Hardware consists of the tool that consists of the technology in the form of physical objects, and it is easier to observe, therefore having a faster rate of adoption than software, which is strictly just the information base of the tool. Similar to trialability, field days and conventions are a good opportunity for potential adopters to observe results and benefits of innovations like drones. Also similar to trialability, observability positively affects the rate of adoption. Higher observability equals faster adoption, and vice versa. Now that you hopefully have an understanding of a small part of Rogers' diffusion of innovations theory, let's do a short assessment to test your newfound knowledge. Question 1 is a true or false question. Compatibility is specific to the adopter's goals, beliefs, experiences, and values. The answer to this question is true. Assessment question number 2 is, which of the following deals with visibility of innovation results? A, trialability, B, observability, or C, complexity? The answer to this is B, observability. The third question is another true or false. Relative advantage is the least powerful predictor of rate of adoption. The answer to this is false. Relative advantage is actually the most powerful predictor of rate of adoption. The fourth question is, which of the following attributes is negatively associated with the rate of adoption? A, complexity, B, trialability, or C, none of them? The answer to this question is A, complexity. The fifth and final assessment question is, which of the following attributes includes experimentation on a limited basis? A, relative advantage, B, compatibility, or C, trialability? The answer to this question is C, trialability. Thank you for taking the time to watch this instructional video. I hope you found it not only helpful, but interesting as well. I have cited the references used here on this slide, and I will also attach a handout in the description of this video posting to summarize and define the content which was covered. Thank you again.